Hi students. So yesterday in our class the concept of integrals we have came across what are integrals, what is integration and some of the geometrical representation of an indefinite integral. So all these ideas we have came across in our last video. So today in this video, so let us move to the next concept, that is the some properties of the indefinite integral. So we came across what are indefinite integrals. So now let us understand some of the properties. So the first thing, as we know that the process of integration as well as differentiation both are the inverse process. So based upon this one there are few properties, like saying the first property, what it says means if I differentiate and integrate any of the function, so the differentiation as well as integrating one function, so integration, so that's why I have represented dx here. So if I differentiate and integrate the function simultaneously, the function is that itself, because both are inverse process, cancels each other. So we are not cancelling like this, since they are inverse process, it is just a say. Or we are saying, suppose if I integrate and then differentiate any function, if I integrate and differentiate any function, means at that time also the function will remain as it is. So here differentiating and integrating, so that is equal to f of x. Here integration is later, first we differentiate then integrate, so plus c. So where c is some arbitrary. So this is the result. So how I am going to prove this? How I am going to prove this result? Suppose if I consider, let f be the antiderivative, it may be the antiderivative of f. So antiderivative of f means, what does that implies? If I differentiate f of x, if I differentiate f of x, I am going to get the small f of x. So f is the antiderivative of f of x. Or suppose if I integrate f of x, what I am going to get? F of x plus c, where f of x is the antiderivative of small f of x. So this is what this statement is saying. So this statement, one thing representation in the differentiation, the same thing is expressed in terms of the integration. So I'll consider now the thing, that is differentiating and integrating f of x. So first thing, integrating f of x with respect to the variable x. So what are they, what we are going to say, since I considered f as an antiderivative of f, so integration of f of x dx, what it gives? It gives differentiation of f of x plus c. So I have done first the thing which is within this flower bracket. So for integrating, first I have integrated this f of x. So integration of f of x is f of x plus d. So differentiation is kept as it is. Now if I differentiate this f of x, what is the differentiation of this f of x? Differentiation of f of x is small f of x plus differentiation of any constant is 0. So it implies f of x. So by differentiating and integrating any function, we are going to get that function itself. Similarly, you can think of here also, integration and differentiation of f of x, what does we are going to get? So clearly differentiation of f of x, it is nothing but f dash of x. So integration and differentiation of an function, we are going to get f of x plus c. So this is how we are going to represent. So the proof of this theorem is not that important, but understand the concept. If I differentiate and integrate any function, so that differentiation and integrations are there simultaneously, means we are going to get that function itself. Suppose if I need to explain this one to an example, means if I consider a function f of x is equal to x square. Suppose if I differentiate and integrate that function x square dx. So what is the integration of this function? First thing, So the integration of that function, we know that x power n means it is nothing but x power n plus 1 divided by n plus 1. Here n is 2, so n plus 1 becomes 3 divided by 3. So here 1 by 3 is constant. Differentiation of x cube. What is the differentiation of x cube? 3 into x square, where 3 get cancels, we are going to get x square itself, that is our f of x. That's what differentiation and integration of any function gives us, that function itself. Suppose if I integrate and differentiate that same function only. So first thing, if I differentiate this function, what way I am going to get? So 2x I am going to get. So now here 2 is constant. If I integrate x, what I am going to get? It is nothing but x square divided by 2. 2 get cancels, x square, which is our f of x itself. So this is how you can understand the meaning of this one through an example. So the next property, what it is saying is, suppose if I consider any two indefinite integrals such that the derivatives of these two indefinite integrals are same. Suppose if I get such a way, that is two indefinite integrals whose derivatives are same, means then they belong to the same family of curve, and hence and so they are equivalent. So the two indefinite integrals, suppose if I consider that two indefinite integral, as one is integral f of x, another one is integral g of x. What they are saying, the two indefinite integral with the same derivative. So the derivative of these two indefinite integrals are same. So what is the derivative? That is d by dx. The derivative of this one is equal to the derivative of this two. So now integral, that is indefinite integrals, are integration of f of x dx and integration of g of x dx. These two are two different indefinite integrals with the same derivative. So that same derivative means this implies, that implies like this. Suppose if we are having like this type of two indefinite integrals with the same derivatives, they are saying these two are belonging to the same family of curve, and so they are equivalent. So how I can justify those things? You can look here carefully. So the given data, I have written it in the form of an equation form. Now if I bring this differentiation of integration of g of x dx to the left hand side, what I am going to get? D by dx of integration of f of x dx minus d by dx of integration of g of x dx, which is equal to 0. So by the algebra of derivatives, I can write this one as d by dx of integration of f of x dx minus integration of g of x dx. So by the algebra of derivatives, I can write this one. But we know that when is differentiation of the certain thing is equal to 0, when the differentiation of, if I consider any constant, of k or c, if I consider any constant, means differentiation of constant is equal to 0. So here we are going to get differentiation of something is equal to 0, means what does that implies? Whatever there within this brick bracket, that is equal to constant. So I am taking, so according to this one, I mean the statement, that is differentiation of any constant is equal to 0. Here differentiation of something is equal to 0 means that something must be equal to the constant itself. So that constant, that is integration of f of x dx minus integration of g of x dx, I am taking that constant is equal to c, where c belonging to some real numbers. Now if I rearrange this one, what it happens? Integration of f of x dx is equal to integration of g of x dx plus c. So clearly g of x plus integration of g of x plus c, this one is belonging to some family of curve, so that these two family of curves are identical. That is integration of f of x plus c1, where c1 belonging to real number, and integration of g of x plus c2, where c2 is belonging to set of some real numbers. Clearly these two are the families of the curve which are identical here. So since these two are a real number, if I Here also if c1 is there, if I bring that one, c1 plus or minus c2, we are going to get both are real numbers. So in together I have represented it with the c. So this 2 becomes what? The two identical curves. So clearly integration f of x and integration g of x, both are indefinite integrals which are equivalent. The next property, what it is saying means, like in the algebra of derivative, here also integration of f of x plus g of x dx is equal to integration of f of x dx plus integration of g of x dx. That means the integration has splitted along with respect to their function. So how I am going to prove this one? Suppose if I consider the LHS and if I differentiated on both the sides, that means d by dx of integration of f of x plus g of x dx. So in differentiated the LHS. So differentiating the LHS, what it happens, since by the algebra of derivatives we know that d by dx of integration of f of x plus d by dx of integration of g of x. So I have differentiated on both the sides. So this was our thing. So differentiating on both the side means here also differentiating, here also I am differentiating on both the side. So what happens here? Differentiating on the both the side means here it comes like this in the beginning. So differentiating on both the sides, since by the algebra of derivatives it goes in this manner. So clearly differentiation and integration of any function, we are going to get that function itself, f of x plus g of x. Here differentiation of integration of a function, I am going to get f of x. Differentiation and integration of a function, I am going to get that function itself. Here writing dx, it is must and should, guys. Don't forget to write this one, otherwise it is completely wrong. If you use the integration means function followed with respect to dx is must and should, or else it is completely wrong statement. So clearly over here LHS is equal to RHS. Thus integration of f of x plus g of x dx is equal to integration of f of x dx plus integration of g of x dx. So we will use this type of algebra of derivative, I mean integration, in while solving some of the problems. Similarly, for the linearity, if I consider some any real numbers, say k, means then k into integration of k f of x dx, this is equal to k times integration of f of x dx. So again if I differentiate on both the side, it becomes like d by dx of k f of x dx is equal to differentiation of k integration f of x dx. So first if I try to solve the right hand side, what it happens, if I differentiate and integrate k f of x dx, it becomes differentiation integration, so k f of x, that function itself. So similarly if I try to solve the right hand side, what it happens, differentiation of constant and then function. So constant I can keep it outside, then differentiation and integration of f of x dx. What does this implies? Differentiation and then integration, so k into f of x. So k into f of x, clearly by differentiating on both the side, both our LHS is equal to RHS. So I can say that integration of k f of x dx is equal to k times integration of f of x dx. So these two properties, it can be used for if there are infinite number of functions. So here we have explained it for only two functions, the f of x plus g of x. Suppose there are three functions also, means f of x plus g of x plus h of x, at that times also the integration can be done by from one component and then next another component and then next another component. Similarly here also if there are more than one constant like k1, k2, k3, so at that time also you can split it and try to do it by yourself for the n number of real numbers also. So now let us try to understand some of the comparisons between the differentiation and integration. So comparison, what we can compare? So clearly if I differentiate or integrate means both these differentiation and integrations are done upon the functions itself, because integration, even this one is also one function. If I differentiate means even differentiation is also going to take place on the function itself. So both differentiation and integrations are taking place upon the function itself. And the next is algebra of derivatives and integration. That is, if I, as I explained here in both the cases, so if I am going to differentiate any linearity of the differentiation or the linearity of the function, that property, that is differentiation of k of f of x, I can write it as k times differentiation of f of x. Similarly, I can do it for the integration also. You can see here itself. So the property of linearity is satisfying for both differentiation as well as for the integration. The next thing what I can say is, suppose in case of differentiation, if I take the differentiation of certain function and if the derivative exists for certain function, means then it is a unique one. But when it comes to integration, if I take the integral, means it is not an unique. It is not unique because it is varying with the constant, integration of constant up to writing. If I integrate, say f of x is equal to x square, if I integrate this one, means what it happens, integration of this one, so integration of this one, I am going to get x cube by 3 plus c up to here, up to the sum of writing the integration constant, up to here the integration of any function, it is unique. But after writing plus c, the function is not unique because the integrals, it is varying with the value of c. So integrals, after doing an integration, the what we are got the integral, it is not unique like the we are talking about when we get a derivative, it is unique, what we say that one, it is not like that. And then the geometrical representation. If I talk about a geometrical representation, means in the derivatives, differentiation, means what does a derivative is going to say, the derivative, that is dy by dx, it is going to say that it is a slope of a tangent of a given curve, slope of a tangent of the given curve. But what does the indefinite integrals geometrical representation is going to say, it is saying that is indefinite integral, it is going to give the family of the curve. So we are going to get a family of the curve. And suppose at one particular point, if I say at say x is equal to a, that point, if I draw the line for x is equal to a, I am going to get a line which is perpendicular to the x-axis. So at that point in each curve x is equal to a, that point is this one. So at that point, if I try to draw the tangent, means all those tangents, that is nothing but this is the dy by dx at the point a in this curve, that is dy by dx at the point a in this curve, this is the derivative of the point at a in this curve. So all those tangents at the point x is equal to a, all those tangents are parallel to each other. So that is what a geometrical representation of indefinite integral is going to be said. So if I talk about a polynomial function, means if I talk about a polynomial function, so in the derivatives, so if I differentiate any polynomial function, what the derivative I am going to get. Suppose if I differentiated the polynomial function, say x cube, what is the derivative of x cube? It is 3x square. So the power of the function and the derivative, it is reduced by power 1. So in the derivatives, the power of the polynomial function is reduced by 1. But when it comes to the integration of an polynomial function, means suppose if I integrate the same function x cube dx, means what is the integral of the function x cube? It is x to the power 4 divided by 4 plus c. So clearly the power of the polynomial function, it is increased by 1. it is increased by 1. So upon differentiation, the power of the polynomial function is reduced by 1. Upon integration of a polynomial function, the power of the polynomial function is increased by 1. So this is one of the comparison between the differentiation as well as the integration. So next is, when I am talking about the differentiation, I can talk about the derivative at a point. I can talk about what is a derivative at a point. I can talk at a point what is the derivative of that function. So if at that point, what is the derivative means, it is nothing but if I draw this curve, what is the derivative at this point means, what you are going to say, it is nothing but if I draw the tangent means at that point, the slope of this tangent of a line at this point is nothing but the derivative at a point. So I can talk about the derivative at a given point. But when it comes to the integration, we cannot talk about the integral at a point. We cannot talk about the integral at a point. We can only talk about the integrals within the range of an interval. So we can talk about the integrals upon only the range of an integral. So regarding this in detail, you are going to study in this chapter. So I am not stressing too much here upon this one. I am just giving some comparison so that you can get some idea. So in the integrals, we cannot talk about what is the integral at a point. We can talk about the integral over the range of an interval. And the general thing which we all know, that the integration and differentiation both are the inverse process, because integration is an inverse of an differentiation. So these are some of the comparisons of the differentiation as well as an integration. So understand it. I have even explained it through some of the examples also. Try to catch what is the comparison between differentiation and integration. Now find the following integrals. Here are some of the examples how we are going to find the integrals. Now we have already know the formulas of finding the integrals. So by using those formulas, let us try to find the integrals of these given functions or these given questions. So first thing is integration of x cube minus 1 divided by x square dx. So let us first simplify this one. So what happens, x cube divided by x square, since it is in the denominator, this one x square is belonging to both the thing also. So x cube divided by x square minus 1 divided by x square dx. So now what it happens, x cube divided by x square. So here from this what happens, square 2x get cancelled, so the remaining is x itself minus 1 divided by x square. I can write it as x to the power minus 2 dx. So by the algebra of integration, I can write it as integration of x dx minus integration of x to the power minus 2 dx. Now we know the formula. What is that formula? Integration of x power n dx. What is the integration of x power n dx? It is x power n plus 1 divided by n plus 1. So here in place of n I am having the power 1. So what happens, integration of x power 1 dx, it is nothing but x square, x1 plus 1 it is 2. So x square divided by 2 plus c1 minus again integration of this one. Here in place of n we are having minus 2. So minus 2 plus 1, what it happens, minus 1. So x power minus 1 divided by minus 1 plus c2. So now what happens, it is nothing but x square by 2 minus into minus, it becomes plus x to the power minus 1, it is nothing but 1 by x plus c1 minus c2. Here c1 is also one constant, c2 is also constant. I am calling this one as equal to x square by 2 plus 1 by x plus c, where c is nothing but what, it is nothing but c1 minus c2. So if we are doing like this problem, for each integral no need of writing this constant for every time. After getting the final answer, at the last you can write one single c. So that single c itself represent whatever the constant you needed to be written in each of the integrals. You can try to right at the last of that. What is that? I mean writing this integration constant. So similarly there is another question, that is integration of x to the power 2 by 3 plus 1 dx. So again it is followed with the same step. So integration of x to the power 2 by 3 dx plus integration of 1 dx. So what it happens, integration of x to the power 2 by 3 dx, so it is in the form of x power n dx. So what it happens, integration of x power n dx is equal to x to the power n plus 1 divided by n plus 1. In place of n we are having 2 by 3. So what it happens, x to the power 2 by 3 plus 1 divided by 2 by 3 plus 1 plus integration of 1 dx. So integration of 1 dx is nothing but integration of dx. So integration of dx is x itself plus c. Now let us simplify this one. So where we are using this c in which step means after integrating the step. So after integration we are using that c in the next step itself. So what it happens now, you are simplifying 2 by 3 plus 1, 3 is the LCM, 3 ones are 3 plus 2, it is 5 by 3 divided by 5 by 3 plus x plus c. So even you can keep your answer in this format also, or else you can keep it in the form 3 by 5 x to the power 5 by 3 plus x plus c. Even you can keep your answer in this format also. The next thing is integration of x to the power 3 by 2 plus 2 e to the power x minus 1 by x. So again with the property of that third property, the integration is splitted to each of the functions. So integration of 3 by x to the power 3 by 2 dx plus integration of 2 e to the power x dx minus integration of 1 by x dx. So what it happens, it is in the form of x to the power n dx. So it becomes x to the power 3 by 2 plus 1 divided by 3 by 2 plus 1 plus 2 is a constant, I can take it outside. Integration of e power x is e power x itself minus integration of 1 by x. What is the integration of 1 by x? It is nothing but log of mod x plus c. Now let us simplify this one. So what is the simplification? X to the power 3 by 2 plus 1, 2 is the LCM, it becomes 5 by 2 divided by 5 by 2 plus 2 e to the power x minus log of mod x plus c. Even you can write it as 2 by 5 x to the power 5 by 2 plus 2 e to the power x minus log of mod x plus c. So this is the integral of a given function, or upon integration of a given function I got an integral like this. So this is how we are differentiating a given function to get the respective integral by using the given formulas, or the formulas which we have already known. So now let us try to get the integrals of some of the trigonometric functions. So how we are going to get? So the integration, the first one is integration of sin x plus cos x of dx. So I can write it as integration of sin x dx plus integration of cos x dx. So what is the integration of sin x? Integration of sin x is minus cos x plus what is the integration of cos x? It is nothing but sin x plus c. So this is the integral of a given trigonometric function. Similarly we are having the another question. So that is integration of cosecant x into cosecant x plus cot x dx. So what I am doing first is I am multiplying this cosecant x to both the terms. What it happens, it becomes cosecant square x plus cosecant x into cot x bracket enclosed within the bracket dx. So now by the algebra, that is integration is splitted to each of the terms. So it becomes integration of cosecant square x dx plus integration of cosecant x into cot x dx. So now what is the integral of integration cosecant square x dx? So integration of cosecant square x dx, it is nothing but minus cot x plus integration of cosecant x into cot x dx. So integral of this one is nothing but minus cosecant x plus c. So I can write it as minus cot x minus cosecant x plus c. So this is the integral of a given function or a given integrand. The next function is, that is, integration of 1 minus sin x divided by cos square x dx. So I need to find the integrals of this function. So how I am starting is, as I said, this cos square x, it is for both the terms in the numerator. So I will write it as 1 by cos square x minus sin x divided by cos square x into dx. So 1 by cos, it is nothing but what? 1 by cos, it is nothing but secant. So 1 by cos square, it becomes integration of secant square x. Here sin by cos square, it becomes like sin x divided by cos x into 1 by cos x. Sin by cos, it is nothing but tan x. 1 by cos, it is nothing but what? It is 1 by cos is nothing but secant x. So the simplification of this one is nothing but secant square x minus tan x into secant x. So now this integration is splitted to both the term. So integration of secant square x dx minus integration of tan x into secant x into dx. So what is the integral of secant square dx? So integral of secant square dx is tan x, and integration of tan x into secant x, it is nothing but secant x plus c. So this is the integral of a given function. So the next question is, we need to find the antiderivative f of small f such that the f of x, it is given as what? F of x is equal to 4x to the x cube minus 6. This is the function they have given. We need to find the antiderivative of this function such that they are saying f of 0 is equal to 3. So how we are going to find it? So clearly they have given the function as 4x cube minus 6. To find an antiderivative means what it implies? It is nothing but integration of f of x dx, which is nothing but integration of 4x cube minus 6 dx. So what is the integration? That is nothing but 4 into integration of x cube dx minus 6 integration of dx. So what it implies? 4 integration of x cube dx, it is nothing but x power 4 divided by 4 minus 6x plus c. So 4 get cancels. The antiderivative is x power 4 minus 6x plus c. This is the antiderivative. So they are saying itself the antiderivative is capital F. I am calling this one as capital F of x, which is equal to x power 4 minus 6x plus c. What they are saying, we got the antiderivative right now here. They are saying f of 0 is equal to 3. So as I said in the beginning, in the previous video of explanation, we can get the value of c when we are having, or when we get one point. If they given any point means we can get the value of c. See, you can see here, we know the antiderivative and they have given one point. Now substituting that point, that is x is equal to 0, f of 0 is equal to 3 means what does that implies? When x is equal to 0, f of 0 is equal to 3. So substituting that one, f of 0 is equal to 0 minus 0 plus c. What is the value of f of 0? It is 3. So now what I got the value of c as equal to 3. So this was our antiderivative. So the antiderivative of the given function is equal to x power 4 minus 6x plus 3. Substituting the value of c in this equation star, or in this equation star, I can get a perfect or one antiderivative or a unique antiderivative of a given function at this point. I mean, when they have mentioned that point, I can get the one antiderivative of a given function. So this is how we are going to find an antiderivative when the function is given and when points are given. So this is how we are going to solve the trigonometric as well as polynomial functions are given. So this is an explanation I am going to cover up in this video. Suppose if you have any doubts in any of the problem solving based upon the integration, means you can ask me at any time. Suppose if you are clearly understood with this concept, means you can try to solve the exercise question 7.1. so I am going to cover this exercise in the next video. So that's all regarding the today's class. Thank you, students.